Hi. Okay, so I think we'll just start now. Okay. Okay. Hey everybody. I'm Clarence. Today the session will be about machine learning. Just to get a quick sense of the room. How many of you have worked with machine learning before? Okay, so that's a good number. How many of you have used one of those machine learning AV softwares before? Okay, that's not a lot. Pretty good sign. So this talk is about how to bypass machine learning systems, and it's still a little bit early in the whole ecosystem now. I think machine learning has started to become a big buzzword in the last few years. What I was curious to know was how many companies are using these terms like deep learning, adversarial machine learning, adaptive systems to try to market their products. If you've been to expo floors at big security conferences, you would have seen at least a dozen companies claiming to do something crazy. So what I did was I just scraped the short snippets of company descriptions at these expos, mainly RSA and Black Hat, to see how many companies actually claim to do such things. And there's an interesting trend over the years. From 2012 to 2015, you can see a pretty large increase from about 4 to 24 at its peak. 2016, it kind of died down a little bit, maybe because people started realizing that it's actually bullshit. So I have a quick short demo to show what machine learning can do and how a system that uses machine learning for image recognition is actually bypassed. This is actually a Czech reader. So in the 1990s, there used to be some pretty janky technology that uses deep learning to recognize digits on checks that you would write to your bank, because the quantity of checks that the bank would receive would be so large that it was just impossible for human tellers to do all the work. So these machines would basically scan the checks and then read these numbers that were basically handwritten digits and try to parse out the digits from them. So here I have two examples of checks. One is a normal one, and one is the adversarial example, which is supposed to generate the wrong output through a deep learning system. And so I've just like a short piece of code using a model that I've pre-trained, prototype.checkpoint. And what this does is just basically extract the digits out from the check. It's a very naive example. I'm just taking a particular area of the scan image, and then what I'm doing is I'm passing each digit through the model, and then the model will basically tell me if this is a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So I'm just running the code Python readcheck.py filtcheck norm. This loads the model from what I previously trained, and it reads the digits 937800, which is, if you actually look at the image itself, makes sense, 9378.00. Okay, and so let's run it through another image, filtcheck adv. And so this image looks pretty similar. I'll show you again later, but then the digits that it reads using the same model is actually different. Let's check it to see how different it looks again. So this is the adversarial image. It says 9378.00. A human will be able to read it as such, but actually gives a different result. So that's just a quick teaser of what this presentation is going to be about. Adversarial machine learning is a field that's still actively in research. There's papers published almost every week in this area. Researchers, mainly in Google Brain, OpenAI, and the University of Pennsylvania, are working on this. So what does it mean to hack machine learning? I think a lot of you in this room are what we consider hackers. I think you have strong infosec skills. You like to do stuff. You like to actually make things break. And so I think that the security industry needs to move in the direction of statistics and machine learning, because more and more systems in the world rely on machine learning for critical purposes. So if you can think of self-driving cars, if you think of some security systems that make use of the adaptive properties of machine learning to detect polymorphism in the adversaries, a lot of things that we rely on in the world are slowly becoming more intelligent and starting to rely on machine learning. So if we want to effectively evaluate the security principles and the vulnerabilities of such systems, the security industry needs to gather the relevant skills to do that. So deep learning, it's not a new toy at all. It's developed in 1943 actually, and like many things, it was developed by funding from the DoD. The reason why it's so popular now is because there's just much more data everywhere. The amount of data that we're generating in the last 2 years, I think, if you remember this very popular anecdote, is greater than the amount of data that we generated as a whole civilization prior to that. And it's revived due to improvements in computational hardware. Deep learning or neural networks or any kind of machine learning actually is very computationally intensive because it's a pretty brute force method of computing intelligence. With GPUs, for example, you can compute multiple concurrent matrix operations concurrently, and this just greatly improves the speed at which you can generate intelligence with machine learning. And there's a popular myth that deep learning is modeled after how the human brain works. I think this is great marketing. You know, like if you can code up the human brain, then of course the possibility that a machine can achieve human sentience is much greater than before. But we'll come to see that actually deep learning is much simpler than what we think the human brain is. And actually, do we really know how the human brain works? I'd argue no. And I think a lot of research shows that there's no agreeable way that the human brain works that researchers can really conclude upon. So deep learning is everywhere. Machine learning is everywhere. I think all of us have interacted with deep learning systems at such point, if not at every day in our lives. Who uses Google Now or Siri or some kind of speech recognition software on a daily basis? Okay, that's a good proportion. I think I tried to use Siri a lot in the past, but then it started to not really work well. And there are some papers describing the way that speech recognition works today and why, as it learns the human's ability to enunciate words, the speech recognition model actually breaks down more and more. So machine learning isn't a monotonically improving piece of software. If the improvements encoded inside the machine learning model are not actively being managed by a human or being actively processed and pruned, then actually the efficacy of such software it can go down. Self-driving cars, for example, are also a very popular application of deep learning. Most self-driving cars are just made up of certain sensors and the cameras. So what this does, it just takes the surroundings as input and it tries to recognize objects. And object recognition is one of the core capabilities of deep learning. What it does is it just takes in an image and it tries to recognize any object taking in arbitrary pixels. In about March of this year, the World Go champion, the board game Go, was beaten by Google's DeepMind, which is based off a deep learning algorithm using LSTMs, and we'll go a bit more into that later. Some security systems have also famously used deep learning to achieve pretty good results. An example is Invincia's malware detection system. This uses some kind of pretty iffy graph processing algorithms to detect clusters of activity. So why would someone choose to use deep learning over just traditional machine learning? Or when I say traditional machine learning, I'm referring to things like linear regressors, I'm referring to things like SVMs or clustering algorithms. The primary reason is because deep learning represents a way of automatic feature learning. So what that means is that if you have an input, let's say you have an image, and this image consists of pixels, and each of these pixels contains maybe RGB values between 0 and 255. How do you select the relevant features to feed into this model? A big problem in machine learning is dimensionality reduction. And the reason we do dimensionality reduction is, number one, because of efficiency. If you were to learn every single feature of every single input that you feed into the model, then your model will be very inefficient. So there must be some decision points in any particular input that would help the model make the same decision as it would have if a human were to look at an image and recognize that this 9 is a 9 because there is a circle on the top, and then there is a curve from the right to the left on the right of that circle. And deep learning also presents one infrastructure for multiple problems, sort of. If you think of other machine learning models, you kind of have to write different pieces of code to try different pieces, to work on different problems. And deep learning represents a single infrastructure, which is just a multi-layered neuron network. And this can promise to solve many different kinds of problems with just one piece of code. And also, with problems becoming larger and larger, you can perform hierarchical learning and distribute this workload among different nodes and across an entire cluster, which also presents itself as a very alluring benefit to using deep learning over some other algorithm like clustering algorithms that cannot be efficiently distributed. But it's definitely not one size fits all, as we'll kind of see. So this is what a standard neural net looks like. This is a 453 neural net architecture. 453 simply means it's a 3-layer network because it's 4, 5, and 3. And the first layer has 4 input units. The second layer, which is the hidden layer, has 5 units. And the last layer, which is the output layer, has 3 units. So what each of these units are, they're just activation functions. They can be very simple linear functions, any kind of function that basically allows you to turn the unit on and off. So one of the most common functions is just a sigmoid function, which just means that if it is below, if the value of the input is below 0, then the output will be 0. If the value of the input function is above 0, then the output will be non-zero. It will be positive. And so let's just zoom in on one particular path, which is the important one. Every time you input a feature vector into a neural net, it will run through the input layer, it will activate the activation function, and then each link between layers will have a weight W associated with it. And when this is passed through the input layer and goes to the second layer, it'll basically be multiplied by the weight, and a bias will be added to it. And this will go through the network successively until it reaches the output layer. And then, as you can see here, for example, the output is 17, 28.5, and 4.5. So this is what we call the logits, or the prediction vector. And the largest of which, so we feed this prediction vector through a softmax function, which is just basically a normalization function that assigns a probability to each output. And so you see in this case, 0.57 is the most probable output. And so if you can think of each position in this vector as a output class, this neural network actually predicted that the value for this input is 1. But the correct class is actually 0. Let's look at this again. This is the first step which I just described, the feed forward step. But in the case that there's an error, for example, here again, the correct answer is actually 0, but the predicted class is 1. And then we go to the backpropagation step, which is the crux of deep learning. The model made a wrong decision. We have to calculate the error, and we have to assign blame. Deep learning is all about assigning blame, and you have a network that learns things. So you assign blame to different units in the network by backpropagation, tracing backwards to find the units that contributed to this wrong prediction and how much they contributed to that total error. You penalize those units by decreasing their weights, by decreasing that value of W, so that in the future, if the same input was fed into this network, then those units would be less responsible for the amount of decision making that this network would make. So beyond just simple multi-layer perceptrons, which is what I just described, there's also more complicated ways to optimize the predictions that neural nets make. There's this thing called convolutional neural networks, which basically is just a way to correlate features that are geographically correlated. So for example, if you're looking at an image, this is a pixel vector. It's a pixel matrix, and a convolution is just a kernel that you put on top of the image and shift it around such that you'll get a single result for each overlap between the kernel and the input matrix. And this just means that when you're looking at matrices of pixels, you won't have to look at every single pixel as a different input vector. You'll be looking at every single group of pixels as a single value. So convolutional neural networks allow us to do layered learning. If you know about facial recognition, the lower layers of the network actually recognize very fine features because the convolution kernels that are overlapped with the original input image are able to look at very fine features and are able to group very small features together. So if you can see on layer 1, which is at the very bottom, you can see things like eyelashes, you can see things like wrinkles on the skin. But as you move up, when you put the convolution over the previous layer's convolutions, then you're able to see higher level features like the actual eyes, your eyebrows, and things like that. And when you feed that up into a higher layer, then you're able to see much more abstract features like the shape of the face and whether your face has a mustache or not. And this is exactly how digit recognition or character recognition works. This is one of the most famous and early neural networks that successfully had good results for digit recognition. And a different kind of neural network is recurrent neural networks. It's just a deep neural net with a feedback loop. So what this means is that instead of learning each particular input as its own vector, the previous inputs also come into play. Previous time steps feed into intermediate steps and final values of the next time step, and it introduces the concept of memory into neural networks. So instead of learning just images and being able to predict what is this input, you're able to predict what comes next, and based on patterns in the past, you're able to predict future patterns. So for example, something that makes use of recurrent neural networks would be a text generation engine. Based on, let's say you train a model on the English language or popular language, then you're able to see that if a Y comes first, then it is probable that an O would come next. And then if a Y and O was previously existing, then an L would come next. And to make good predictions, we need more context. So long-term memory capabilities without extending the network's recursion cause the birth of long short-term memories, which is the core of AlphaGo, which is what beat the world's Go champion. So speech recognition has been powered by deep learning for a long time. This is just how some of the popular speech recognition algorithms have progressed over the years. The different colored lines just represent different kinds of data sets that you would use for speech recognition. The black one represents red speech, which is one of the most clear and clearly enunciated data sets ever. And the red ones is really the holy grail. It's conversational speech. And this data set, I think, actually is from a speed dating recorded conversation. So I had the chance to listen to it, and it's pretty interesting what they were talking about. So the core representation is about how to defeat machine learning and how to bypass such systems. There are some general concepts that you can use to power work like that. I think different machine learning models have different nuances and different ways that you have to look at it to generate adversarial input or to poison the model in a way that would cause an unexpected output. But there are just certain overarching principles that you should know, and I think it's important, and that's what this presentation is about. So one of the most popular data sets for image recognition is the CIFAR10 data set. It's just basically 60,000 really, really small images, each belonging to one of 10 classes. So here I have two sets of pictures, one of a dog and one of a car. And so, it's very pixelated because these pixels are 10 by 10. These images are 10 by 10 pixels large, and the reason why they're 10 by 10 pixels large is because it's to facilitate the training of the model. If you have ever trained a machine learning model before, you'll understand that training these models take a lot of time, and the more features you have, the more time it takes, and it actually increases exponentially. So having a small number of features enables you to do research fast and enables you to train model quickly and to have smaller and shorter iterations. And so you see, like when we evaluate the dog and the car, in this case we're just evaluating the dog first. Each different example, dog norm, dog at 10, and dog at 1 actually gives different results. And dog at actually means dog at is actually the original dog image with some adversarial input added to it. So we see the same thing for the automobile. We do automobile at 1. Which looks the same. It says it's a cat. So this is a black box attack, which means that I don't know anything about the internals of the network. This is a pre-trained model that I downloaded from the TensorFlow codebase. So let's just look at the differences between each of these images. We're just going to read in these images and see how different they actually are. To the human eye, they don't look that different. If we were to just look at these with our eyes, then we can see that they look like images that are the same with just a little bit of noise added to it. So this is the pixel matrix. The shape is 32 by 32 with 3 channels RGB. So we see that each pixel has the minimum value of 0 and a max of 255, which is expected. So we're reading in the at1 image for the dog. Okay, so this is also a image matrix. It has the same shape as the normal image. And let's look at the difference by subtracting the adversarial image, by subtracting the normal image from the adversarial image. So we see that there's just very small perturbations in each pixel of +1 or -1 or -2. And to the human eye, you can't tell a pixel 001 and 000 very well. You can't tell them apart, but to a model which actually looks for certain things to learn to recognize that this particular image is a dog, it actually can recognize it and actually makes a difference to what prediction it makes. So we printed out the difference, and it looks like garbage added to the dog image. And that causes the result, this, which looks pretty much the same. So it just goes to prove that your eyes can't really tell apart images that are slightly different. But as we saw earlier, the machine learning model thought differently. Now let's just see dog at 10 to see what the difference between dog at 1 and dog at 10 is. Dog at 10 is basically a stronger perturbation to the original input that we saw earlier. And if we do the same thing by subtracting the original image from, then we see larger perturbations of the input vector. Yep. So we'll come back to that a little bit more later. Let's look at some attack taxonomy to see where the vulnerabilities are in these machine learning models. There are two kinds of, in general, there are two kinds of attacks that you can do on machine learning. One kind is causative and one kind is exploratory. So causative attacks actually require you to manipulate training samples. Machine learning is split into two general stages. One is training and one is testing. So In most models, the training step and testing step are separated. But in some examples that you can see online, for example, in Google Translate, they're actually making use of an online learning system, which basically means that every new prediction that it makes, it immediately takes in feedback from the user to train the model even more. So, for example, when you make a translation and you see that it did pretty poorly, you can right-click and then select the right translation for it according to you, a human. And the model will actually take this input and train its model even more. So this is a scenario in which the training and testing step are interweaved. But in most cases, offline learning, the training step is separate from the testing step. So you would train a model offline, and then you would deploy this model to a web server or somewhere where a user will interact with it. And then if you were to retrain, you have to take in input from other sources to retrain this model based off the old model. So causative attacks basically means that you have access to this training stage, which isn't always the case because these models can be trained privately in your own private servers, and users may not ever have access to this training stage. Exploratory attacks are more powerful in the sense that the users or the attackers don't necessarily have to have access to the training stage. All they have to have is access to the model, to the testing stage, and feed in adversarial examples, and then they can adjust the output that this model gives. And so this is the example that I showed earlier, whereby we didn't have access to the image recognition model at all. We just fed in a different image that was slightly changed, but we were able to force a different output from the model. So why can we do this? The general principle behind this is blind spots. Machine learning models don't learn the same way that humans do. I think when we talk about deep learning, a lot of people seem to think that deep learning systems learn in exactly the same way as humans learn. But humans don't necessarily look at individual pixel values and recognize objects like that. What we do is we look for salient features. We look for features that are telling of what what this object is, and then we remember this, and in the future, if we recognize these same features again, then we would classify the object as such. But this is actually a really, really tough thing for machine learning models to do, because there are just so many rules that we have grown up with, that culture has inculcated in us, that these things cannot be effectively coded into a succinct model. So adversarial deep learning is mainly 3 steps. First thing is to run the input X through the classifier model. And then the second step is to, based on model prediction, derive a perturbation tensor or a perturbation vector that maximizes the chances of misclassification. There are 3 ways of doing this. I'll go into detail later. And the third step is to scale this perturbation tensor by some arbitrary magnitude. The smaller magnitude you scale this by, the less detectable it is to a human looking at it. But also the chances of it actually tricking the model are lower. The larger you scale it by, a human will be able to detect it, but also it'll be able to trick the model much faster. So the very first way that someone came up with for tricking this model is basically to traverse the data manifold to find blind spots in the input space. Adversarial samples are basically pockets in the manifold. So if you can think of all possible pixel variations that make up the image 1, for example, what we want is for every single different set of pixels that look like a 1 to a human to be classified as a 1 in this machine learning model. But that's not actually the case. So this actually just does a brute force attack and searches for pixels that pixel variations that do not result in the correct classification. Then there's also another attack just developed last year that uses linear adversarial perturbation as an attack. Develop a linear view of the adversarial examples, and you're basically using the cost function gradient of the network with respect to the input sample and the original predicted class to derive a sign for which this perturbation should be added to. So, for example, if you take the cost function gradient with respect to x and y, and you find that it is positive 1, then you just basically add +1 to the entire input. And this would more effectively trick the network. And the last one, which is the most effective one, is the Jacobian matrix perturbation way. I won't go into the details of this. There's pretty complex derivations, but basically this just looks at the saliency map of each image. So this is a 28 by 28 saliency map. And you see that the higher the values of perturbation, it means that this network actually looks at this particular pixel more seriously. And if you change, for example, the center pixel by a little bit, it'll be much more effective than changing the pixels on the side by a little bit. So the threat model for this is multifold. Of course, if you have access to the hyperparameters, if you have access to the actual model itself and every value in basically all the weights and biases in the network, then you're able to do a lot. However, if you only know the architecture or if you only know the training data used to train this network, then you're able to do less. And if you don't know anything about it at all, you only have access to the input and the output, then it's basically a black box. So what can you do if it's a black box? This is just a summary of a text. This is the slides we posted later, and you can take a look at them. There's some interesting work done by different people with different assumptions about the adversarial knowledge and the complexity of the attack as a result. So you can do quite a lot with limited knowledge. Throughout this research, I did some experiments on how easy it is to bypass machine learning systems when I didn't know anything about it at all. The most important thing is to make good guesses about the model. Even if you don't know exactly how the model was implemented or you don't know what kind of neural net was used in this model, you can make good guesses. Image classifications most commonly use convolutional neural networks. Recognition engines most commonly use LSTMs or recurrent neural networks because they need to understand a sequence in the input. For arbitrary machine learning as a service models like Amazon ML or Google Cloud Prediction, they use very shallow networks because they need to generalize well. If you have a more shallow network, you're able to come up with more generalized understandings of arbitrary problems. If you have a deeper network, then your model is more likely to overfit. So if you can't guess, you still can do quite a bit. This is the last demo that I have. Capture is someone's cool project that was used to recognize image captures. So the whole point of captures is that you don't want a bot to be able to automatically solve it. But of course, as you might know, there's lots of things that actually solve captures for you. There's even capture solving services like Death by Capture that use some kind of mechanical Turk thing so that someone on the other end of a computer somewhere else in the world can solve the capture for you. But that's not really scalable because like I don't know many people who are willing to sit down at their computers and earn like half a cent per capture they solve. So this actually is a program that uses machine learning and deep learning to recognize images. Even if it looks really convoluted, it's able to give the right results. So let me just run this, just an example of how deep learning capture recognition engines work. So this is a pretty naive example. There are many different ways of training a capture recognition engine. I'm generating these captures that look pretty complicated. Like I would have trouble typing some of these in, and I think a lot of captures in a while are like that. So I'm just regenerating new images just to show that they're different each time. The input characters are just A to Z, so nothing too complex. And what I'll show is that the capture model eval will be able to recognize this, and the training of this model is non-trivial. So I don't own like a really powerful GPU cluster. If you can see, I started training this like July 12th at 5:53 a.m. and by the time this was done, after 100,000 steps, it was July 13th at 9 a.m. So it's more than 24 hours just to train this simple capture recognition system. But the prediction results are pretty good. As you can see, like all the 6 digits did pretty well. So let's test it on these captures that I just generated. It's pretty slow because it's a large model. So it's just using that model for testing. And so each number in this vector represents a letter in the alphabet. And the actual and prediction. So okay, this does perfectly. It doesn't always do it like that. Sometimes there's 0.9s and 0.8s in there, depending on the complexity of the input. So you can see most of them. I mean, all of them have the same actual and predicted values. And that's exactly what we expect because it's just a well-trained model. Well, it better do well because I think $200 on the Amazon bills. So Amazon has two GPU instances, and I think they're $2.20 per hour for spot instances. And yeah, so if anyone from NVIDIA is here and wants to give me some GPUs, thanks. So this is how. So this is a little bit meta because what we're doing is we're generating captchas to trick bots that solve captchas. So if you can think about how this will be useful, captchas are meant to defeat bots. So if you're able to generate captchas that can trick the bots that are designed to solve them, then you've won the game. So these are the same captchas that I generated earlier. We can generate new ones as well, but they're just random generated captchas. What we do is we want to generate the adversarial version of these captchas. So we're doing that here. Live model is just a model that we pre-train on these captchas, and then we are going to generate the perturbation vectors that we will add to these captchas, and then they'll be put into a folder here. So it's also pretty slow because the model is large, but let's just do 10 and then we'll test them. So this is the code to generate the adversarial image. It's 5 lines, literally. And so if you look at the two sets of images, they look exactly the same. I mean, there's probably some gray spots in there with a difference of 1, but you can't really see them with your naked eye. And let's test it on this. So we're going to evaluate these adversarial input. Just feeding in the folder, and then we'll evaluate all the input images in that. Now this is slightly different from the previous example because there are fewer salient features in this entire input. An image is pretty complicated, but if you just look at a printed character, there's actually not that many salient features that you can extract from this. So I would expect the output to be bad, but not as bad as before. So you can see the precision of this is 0.1, 0.2, which means that at every position, at position 0, it predicted 0.1 of the examples correctly. At position 1, it predicted 2 of the 10 examples correctly. Actually, at position 3, it predicted 7 out of 10 correctly. So that's still okay. If you can get past 7 out of 10 captures, it's still okay. But as you can see, just very simply generating capture examples that is able to trick a model that was previously able to recognize captures correctly at a prediction rate of 100%. It's pretty easy to do so. So the black box attack methodology in machine learning is a interesting problem. It's still an open area of research, and what this is transferability. So if you can think of any machine learning model out there that uses an arbitrary way to make classifications, to make predictions, and if you can think of how to generate adversarial examples for each one of those systems, it's actually not that complicated. What people have found empirically is that adversarial samples that fooled model A previously have a pretty good chance of fooling a second model B, even if you've never seen this model before in the past. And these models can be anything from clustering algorithms to SVMs to decision trees to neural nets to linear classifiers to even naive Bayes. And this is just some research that another researcher, Papernut, has done in the past. And this is a matrix of how well adversarial examples trained with another model are able to trick a model that it was not trained with. So if you can see linear regressors that adversarial examples generated by linear regressors can trick SVMs with a 91% chance. And deep neural nets generally have a pretty good transferability rating. If you generate adversarial examples with deep neural nets, you can trick decision trees at a rate of 80%. So that's pretty good. And this means that you don't necessarily need to know how a model was implemented to generate adversarial examples for it. You can just generate it with an arbitrary method or with all and try it out and see what does well. And then you're probably going to be right. If you can't do that, then using a substitute model is a good way as well. What this means is basically you're training a new model by using the black box model's output as input examples. So this was used as a method for distilling models, and this was used very popularly in mobile phones. When you train machine learning models, eventually you'll end up with a model that is gigabytes large. And it's not really practical to put that in a mobile device or your phone because that just takes up too much space, or put it in a cloud service because then it just requires too much computation. So this distillation was a method for distilling the important parts of a machine learning model such that the most commonly used parts of the neural network will be kept, and the least commonly parts that are seldom activated will just be pruned out. And this was just empirically found to be a pretty good way of generating substitute models as well. So transferability is still an open research problem. This adversarial situation in machine learning is possible because of blind spots and differences between the model and reality. But is this model really not learning anything at all? I think that's still pretty much an open problem. So this means that machine learning models are susceptible to manipulative attacks and can be pretty easily bypassed in most scenarios. You shouldn't make false assumptions about what the model learns and how the model learns, and you should always evaluate the model's resilience to adversarial input before you deploy it in critical scenarios. You should spend some effort to make models more robust to tampering, especially if they're being deployed in critical scenarios like self-driving cars. There are some interesting papers published in the past where if you put a stop sign printed on a piece of paper in front of a self-driving car, the car would stop. And if you covered the traffic lights with a piece of cellophane, a human would be able to tell the traffic light is still there, but the self-driving car would not, and would not stop. So to defend these machines, 3 different ways: distillation, you train the model twice, and then you feed the outputs into the second model, and this is able to take out a lot of the data manifold, the blind spots that exist in the model. You can also train the model by using adversarial input. So this is a little bit meta too, but if you generate adversarial input from the initial model and then you use this input to train the model again, it'll perform better. And there's also some other more complicated methods like regularization and loss function methods that can be used to reduce the impact of adversarial input on these models. So what I did was basically have a framework for generating adversarial inputs for machine learning. It's called Pwning. And it's on GitHub. All the code is there. All the code that I used to generate the examples here is online. First presented this at GrrCON this year, and it was pretty well received, and people have started contributing to it. So there's pretty comprehensive write-up on what you can do with this and how to do it. The purpose of this is, of course, to let people know how easy it is to generate adversarial examples and how easy it is to bypass machine learning models, but also to urge people to start to look at machine learning models with a critical eye, like how you would look at Unix systems and hardened Unix systems. You should also do the same for machine learning models, because a lot of critical systems rely on machine learning, and it is pretty scary how many real systems deployed out in the wild can be bypassed with this simple technique. So, as mentioned, train models with adversarial samples for increased robustness is one of the most important takeaways. So please play with it and contribute. And deep learning and privacy is also an interesting area that I think is interesting and needs a lot of research in. A lot of large companies, Google, Facebook, are infiltrating our lives. Google Home and a lot of IoT products that are released by large companies are actually Trojan horses that are used to collect data from us. The more we interact with them, the more data we have, the more data that we send to them. But you can actually extract a lot of personal information out from deep learning models, even though it's unintuitive. So, for example, if there's a voice recognition engine or there's a facial recognition engine that is coded into a machine learning model, such that the model can recognize your face from the raw pixels. Even if the actual pixels are not present in the model itself, you can reverse engineer the model to generate your face from that. And that's pretty mind-blowing to me. So, as I mentioned, this is important because I think many people in the security industry, or even in the machine learning industry, are not that concerned about security or machine learning or vice versa. I think that needs to change, especially in the future where we rely more and more on these systems. And as we place more and more importance on the efficiency of machine learning systems, the efficacy of these systems, and how much we trust their results. So please contribute to the project, check it out, start on GitHub, and that's all I have. Thanks. Any questions? Here. Yeah, okay. So the question is, have I ever tried to reverse engineer the cat detection software to see what the model thinks a cat looks like? The answer is no. I haven't done that much research in deep learning and privacy. I think it's a really cool area. In general, it requires a lot of computational power, because if you can think of how much time it took for the cat software, the cat model to be trained in the first place, and you have to generate examples for how many pixels it takes to generate that cat model. It's actually pretty computation intensive. So a lot of research that's done in the field today is limited by computational power, even though I previously mentioned that advances in computation has caused deep learning to explode. But NVIDIA released a deep learning in a box solution that sounded really cool, but I inquired and it cost $129,000 for that box. So I'm not going to be able to afford that. Okay. Yeah, so that's pretty interesting. The question is, how do I describe the attack used on the Tay chatbot that Microsoft released earlier this year? So I'm not sure how many of you are familiar with the Tay chatbot, but it's basically a learning artificial intelligent Twitter chatbot that was able to respond to people's tweets at it, and then respond to their tweets and learn from the language that they were using. It quickly became a racist, homophobic, Nazi bot, and I guess that's just more of a reflection of Twitter being a cesspool, but I think that's a great example, because this is an example of causative attacks of causative attacks whereby the model is learning in an online fashion and you're unable to prune results really, because there's no human in the loop to help the model learn in the right direction, and without a human in the loop, machine learning models today can't really decipher what it should and what it shouldn't learn. So I guess it was pretty naive when they deployed that, because I mean anything that takes in input from Twitter is gonna end up like that. So not surprising. Here.
Do the techniques that develop the adversarial inputs just identify something that is miscategorized, or can you also make them generate something that is miscategorized to a particular other
Yeah, that's a great question. That's great intuition. There's in the graph that I showed earlier, where made up of different work done by different people. If you can see here, there's a line targeted misclassification. That just means that you're able to choose a target for where the classifier will end up. So that just means that if an image looks like a 1 initially and the classifier correctly predicts a 1, and you wanted it to look like a 7, you can train the model in such a way that you can add a perturbation vector to this image that would make it look like a 7. And source target misclassification is an even more targeted way of doing this. You can make 1s look like 7s and everything else look the same. Yeah. Any other questions? Cool. Yeah, this is great. Thanks for being here. Please go check out the project online. It's Deep Pwning. And if you have questions or if you want to join or contribute, please. Thank you.